Hi and welcome back to class of Design of Machine Elements. I am Hitesh Raiyani, Assistant Professor at LJ Institute of Engineering and Technology. This is lecture 38, Examples of Designs Against Fluctuating Load. So learning outcomes of this lecture is to learn the examples of design of spring when the spring is subjected to fluctuating loads. So consider the problems as given here. A helical compression spring of cam mechanisms is subjected to an initial preload of 50 newtons. Here the initial preload of 50 newtons is given. The maximum operating force during the load cycle is given 150 newton. So here the maximum operating force is given and that is nothing but the Pmax. So Pmax is given 150 newtons and P minimum is given 50 newton. So here the case of fluctuating load and the wire diameter is 3 mm, small d is given, that is 3 mm, while the mean coil diameter is 18 mm. So mean coil diameter means capital D is given, that is 18 mm. The spring is made of oil hardened and tempered ball spring wire of grade VW, and the SUT value of wire is given, that is 1430 Newton per mm square. Determine the factor of safety used in the design on the basis of fluctuating stresses. So here we have to calculate the factor of safety which is used in the design basis on the fluctuating stresses. So first of all, we collect the data given here. Here the P max is given, that is 150 newtons. P minimum is given, that is 50 newtons. Small d is given 3 mm and capital D is given, that is 18 mm. So SUT value is given, that is 1430 Newton per mm square. So this is the given data and we have to calculate the factor of safety. Now to calculate the factor of safety, we first calculate the mean stress and amplitude shear stress. As we know here the case is the fluctuating stresses, and whenever any component is subjected to fluctuating stresses, there are mean stress and amplitude stress. So in case of spring here we have to calculate the mean and amplitude shear stress. So to calculate the mean and shear stress, as we know that for mean stress Ks factor is used and for the amplitude stress the K factor is used. So to calculate the Ks and K factors we need the spring index. So we have a given capital D and small d value, so we can calculate the spring index. So first we calculate the spring index. C is equal to capital D divided by small d. Here capital D is given 18 mm and small d is the wire diameter is given 3 mm. So we can place the value of capital D and small d. We get the value of C is equal to 6. So now we have a spring index is equal to 6. So we can calculate the K is equal, that is Mal's factors. K is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. Here the value of C we have to place as 6. So if we place the value of C in these equations is equal to 6, and we get the K is equal to 4 into 6 minus 1 divided by 4 into 6 minus 4 plus 0.615 divided by 6. So we get the answer K is equal to 1.2525. Now we also calculate the Ks. So as we know the shear stress concentration factor Ks is equal to 1 plus 0.5 divided by C. So by placing the value of C is equal to 6, we get the Ks is equal to 1.0833. So now we have all vectors k and ks. So we can calculate the mean shear stress and amplitude shear stress. So for that we also calculate the mean force and amplitude force. Mean force for the mean stress and amplitude force for the amplitude stress. So we know the mean force Pm is equal to 1/2 P max plus P minimum. So here P max is equal to 150 and P minimum is equal to 50. So if we place the value of P max and minimum, we get Pm is equal to 100 newtons. So in this way we know the amplitude force Pa is equal to 1/2 P max minus P minimum. So if we place P max is equal to 150 and P minimum is equal to 50, we get Pa is equal to 50 newton. So now we have a value of K, Ks, Pm and Pa. So we can calculate the mean stress and amplitude stress. So next is tau m. So tau m is the mean shear stress and we know the formula of tau m, that is equal to Ks into 8 into Pm into capital D divided by pi d raised to q, pi d cube. So here Ks value we have to place 1.0833, which is calculated in previous line, and Pm we calculate that is 100, and D, capital D is given in our problem, that is 18 mm, and pi into small d cube. So small d is also given in our problems and that is equal to 3 mm. So if we place all these values, we get the answer of mean shear stress, that is tau m is equal to 183.91 Newton per mm square. So this is the mean shear stress. Now we have to calculate the amplitude shear stress, and we know the amplitude shear stress, the factor K is used. So tau A is equal to K into 8 Pa into capital D divided by pi d cube. Here the value of K we have to place 1.2525 and Pa we have to place 15 Newton, which calculated in previous slide, and capital D and small d is given in our problems, that is 18 mm and 3 mm respectively. So if we place all this value, we get the amplitude shear stress, and that is nothing but the 106.32 Newton per mm square. So this is the mean stress and amplitude shear stress values, and now we have to calculate the factor of safety. So second things, we have to calculate the factor of safety. Our aim is to calculate the factor of safety, but here the case is in fluctuating stress, and to calculate the factor of safety, we first calculate the mean stress and amplitude stress. Now factor of safety, next we have to calculate, and for that here the relationship for the oil hardened and tempered steel wire are as follows. According to condition, here the condition is oil hardened and tempered steel wire. So for that we know the relations S dash AC is equal to 0.22 SUT. So we have to directly use these equations, and here the SUT is given, that is 1430 Newton per mm square. So if we place the value of SUT, we get S dash S, that is endurance limit, is equal to 314.6 Newton per mm square. Now we have second considerations relationship according to these conditions, that is SS by is equal to 0.45 SUT. So if we place SUT is 1430 Newton per mm square, we get SS by is equal to 643.5 Newton per mm square. So this is the value of SS, S dash AC and SS by we have to use to calculate the factor of safety. So I call back these two equations, two values of SS, S dash AC and SSY. Now here the case of fluctuating stress, and we know for the fluctuating stress the equations tau A divided by SSY upon factor of safety minus tau m, and that is equal to 1 half h dash AC divided by SSY minus 1 half h dash AC. So h dash AC value we have that is equal to 314.6. SSY value we have that is 643.5. Tau A we calculated and tau M we calculated. So only unknown in this equation is the factor of safety, and our aim is to calculate the factor of safety in particular design. So if we place all this value as tau A is equal to 106.32, which is calculated, and SSY is equal to 643.5, and tau M is equal to 183.91, and H-SE is equal to 314.6. So if we place all this value in these equations, and if we solve these equations, we get this is 106.32 divided by 643.5 divided by factor of 50 minus 183.91 is equal to 157.3 divided by 486.2. So further we have to simplify these equations, and if we simplify that, we get 643.5 divided by factor of safety minus 183.91 is equal to 106.32 into 486.2 divided by 157.3, and that is equal to 328.63. So now the 643.5 upon factor of safety minus 183.91 is equal to 328.63. So we can calculate the factor of safety, and if you simplify, we get the factor of safety that is equal to 1.26. So this is our answer required. So factor of safety is 1.26 according to the given design data and subjected to the fluctuating stresses. So in these lectures we learned how to design the spring when spring is subjected to fluctuating stress. In next lectures we learn the design of leaf spring. Thank you.